All right, so welcome once again to 3308C. This is E-Circuits1. And as I guess most of you are also hoping that you are in the right class, I'm also hoping I'm in the right class as well. Right? Something else that happens during the first day of the lecture, at least it used to happen to me as well, that I needed to find out where I'm going to sit. Am I going to sit in the front row, the back row, somewhere in the middle? Because you know that the front row and the back row is kind of always the center of attention, right? So the middle rows have worked out really well for me when I was a student. But yeah, of course, whatever works for you guys. All right, so E-Circuits1, here we are going to learn more about electronic circuits, and I'm going to explain what electronic circuit will mean to each one of us. But before going into the technical details, I'd like to make sure some of these logistics are clear about the class. So all the details related to the class will be posted on Canvas, as all of you already have been using this Canvas website as well as the app. Now, sometimes you have seen that the app malfunctions a little bit if it is on a phone. So always make sure that you also check the web page as well for the latest announcements. Okay, so class locations, as I think all of us already know, this is going to be where our classes is going to be held. I'll be recording the classes over Zoom, and you can also join the Zoom link as it has been posted here on the Canvas. So I would like all of you to attend the classes in person because that's where most of the interaction will take place. But in case you are not able to attend a class, please feel free to join the Zoom link. Also, there is a discussion forum on GroupMe. Again, I'll encourage all of you to join the GroupMe chat so that we can all, if there are any questions, we can always go on and discuss that over GroupMe. Okay. The TAs are also here. The TAs and EPIs, they are also part of the GroupMe chat, and they can help you as and when required. We'll be discussing more about the syllabus today, as well as something that will be important for your labs. So as you know, that this is a 4-credit class, and as part of the 4-credit classes, we have a lab component, which means that we are going to use the MAEB 226 lab. I'll give you the details of how to access the lab, when to access the lab, and so on. But one thing that is important is that we're not going to start the labs till September 15th. So September 15th will be the first day of the labs. Again, that is there in the syllabus. I'll show that once again in a few minutes of time. But within the next few weeks, what I would like you to do is to go ahead and order the parts list. So as part of this particular lab, we are So as part of this particular lab, we are going to use a few electronic components or parts. So this parts list is also uploaded on Canvas. So you can access the parts list over here. Also, it's there as within your lab, or rather lecture 1. So if you go to the lectures, within lecture 1, the syllabus and the parts list, everything is there, placed in the file section. Also, you can find it in the home page over here in the parts list. So what this parts list tells you is some of these components that we need to buy. So of course, in the past, this lab used to work on a different mode where for registering to the class, the students used to be charged extra, and then the department used to pay for some of these parts. But what we noticed over the years that the cost of these parts is only about $25 or so, or maybe around 30. Whereas what was being charged from the students was a little bit more. So that's why eventually the department came to the conclusion that the students are going to order the parts because that will eventually be a lower cost to them. So these are the parts that you need to order. I have created a DigiKey link over here that I'll show in a minute. And as part of the parts or the components that you'll need to order, you'll see that there are very well-known components such as op-amps, which should be very familiar to you by now, because most of you, and I guess all of you, have taken the 31111 class. So there are 2 of these op-amps. There is a Smith trigger as well. there is FET or field effect transistors, and we'll be discussing about field effect transistors in detail in this class. There's also a transistor array, diodes, BJTs, and so on, as you'll see as parts of or part of this list that you have been provided. So if you just click on this link at the bottom, you'll see that all of this, I have created a DGKey cart containing all these components on the first page. The total comes out to be about 24, including shipping. And all these components are currently available. So please go ahead and make sure that you order them as soon as possible. There are a few other components, for example, resistors, capacitors, and so on, which I felt SparkFun was the easier choice, or basically the cheaper option as compared to DGKey. So please go ahead and order these components as well, the resistors and capacitors. Many of you may already have them from your previous classes. If you already have them, you don't need to order more resistors or capacitors. But if you don't, please go ahead and order them as well. And please look into this parts list. There is also a very nice website called Octopart, where you can actually compare the prices of these components over different websites. So in future, if you're trying to order some electronic components, this could be very useful because you get a comparison of what different websites or different portals can give you, including DGKey, Mouser, SparkFun, and so on. All right. So that's going to be the first homework, or the 0th homework, I should say, that please go ahead and order your parts because they will be very important for the labs. All the other, but as I said, that the labs will start on September 15th. Today is August 22nd, so we'll not have any labs till September 15th. The first day of the labs will be September 15th. And please ensure that you have all your components ready by that time. Okay, so we have about 3 weeks, or little more than 3 weeks actually. So please be proactive in ordering the parts, because some of these parts may take a little bit of time to arrive. Okay? Also, you can probably, if you have friends in the class, you can probably order them together, because then the shipping cost goes down, right? So please be smart about ordering the parts, whatever you can do, but just make sure that the parts are here before September 15th. All right. The labs, these are the slots for the labs. You know that many of you already have seen this in your 1.e web, whether you have been assigned a Monday slot or a Tuesday or Wednesday or a Thursday. So these are the 4 days where the labs will be held. The TAs and the EPIs, they will be helping you out with the labs. Some of them are already here. Elliot and Nathan are there. Maybe you guys can stand up so that they can see you. Okay.
Also, Kevin down here.
Oh, Kevin is also here. All right, sorry, I missed you, Kevin. Yeah. So, yeah, I think as many of us are already here, let me show you this as well. So these are the TAs that you have for the course. We have Elliot, who is here. Nathan is here. Kevin is here. There's also Jack and Jose. Jeremiah will not be able to join us for this semester, but I didn't get a chance to remove his name for now because he just informed me right before the class. But we have 5 other TAs who will be helping you out with the labs. Okay. Their email IDs are also mentioned over here. So please feel free to reach out to them, but they are also part of the GroupMe chat. So probably the easiest one, or the easiest way to, let's say, get in contact with the TAs would be to use the GroupMe chat. All right. And the TAs and us, we have been discussing about who will be taking care of which lab section, and we'll post it maybe within a day or 2 on campus. All right, and now everything else related to the lectures and the labs, I'll be posting here. For example, as you see, lecture 1, 2, 3, and 4, the notes have already been posted. I'm also recording each of these lectures, and I'll be posting them on YouTube, and I'll provide the link over here. Right now, this link is not active, but after this class, I'll go ahead and upload and make this link active, okay? And I'll be keep on adding these lectures as we progress week by week. Right now, what I have is lectures 1 through 4, which is basically end of next week. We also are going to start with the homework next week. I'll be talking more about the homeworks and how we are going to submit them in detail. The labs, again, they are going to start on September 15th, and the first lab will be from September 15th to 18th. I've also put all the materials for lab 1 over here. Even though there's quite some time to get started with lab 1, I just wanted, if someone is interested, you can just look into the PDFs that have been provided. Also, there's a lab report template that have been uploaded here on Canvas. So bottom line, I'm going to sort of upload all the documents related to the classes as well as the labs on this homepage. You should be able to find them on the file section as well, but please be on the lookout for any announcements or any new files that have been uploaded on Canvas. Okay. Any questions till this point? All right. So if not, let's formally get started. Again, I'll be repeating some of these logistics in case some of you reach the class late. But in general, I'll be talking about the logistics a little bit and then some technical details about the class. So today is lecture 1, and my name is Vaibhav Chatterjee. I'm an assistant professor at the Department of Electrical and Computer Engineering. You'll be seeing me a lot over this semester, as all of you already know. Now, again, this slide is something that I already showed before. The TAs, 3 of them are already here. Please feel free to reach out to them. If you have any question, please feel free to reach out to me as well. This is my email ID, my phone number, office phone number is also provided over here. So if you have any question, please feel free to reach out. Okay. The classes will be held in this classroom for the JM 280, whereas the lab location is a little bit different. It's in MAEB 226. So please make sure that the lab location is different, and please make sure that you reach your correct lab time or reach the correct lab location at the correct times. Now, in terms of the course organization, I'll be talking about the major topics that we'll be covering in this course, and each topic will include a particular set of homework assignments that will help you to understand the details of that particular concept. There would also be labs, which are kind of almost 1:1 related with the theory that we'll be discussing in the class, and we'll be emphasizing practical applications of the circuits and the components that we'll be learning in the class. All right. Now, the theme of this course, mostly what we'll be covering, what we'll try to cover is practical electronics. And by practical electronics, what do I mean is how do you create circuits to do useful and meaningful things. So sometimes you'll see circuits are imperfect. And if you have some experience working with real circuits, you'll see that if you buy a 100 ohm resistor from the market, it may not be exactly 100 ohm. It could be 95 ohms. It could be 102 ohms. It could be 98 ohms. It's not perfect. So how do you build perfect things with imperfect components? Or at least, how do you analyze the circuits so that you know that there would be some imperfections, and taking care of those imperfections or keeping in mind that there would be imperfections, how do you design perfect circuits? So that would be one of the goals that we are going to learn in this semester. And generally in classes, we assume things are ideal, things are perfect, but that's not what is going to be here. We'll try to make sure that you know a little bit about what's out there in the practical world. And that's what we're going to call design-oriented analysis, that your final goal is to come up with a design that works perfectly in all conditions, or at least the conditions that you want it to work with, right? So that's why the design or the final outcome is more important. The individual components can be imperfect. There could be a lot of errors associated with each of the components, but what should be a strategy and how do you eventually come up with a good circuit? That's what we are going to learn. Of course, there is a prerequisite to the class, that is EEL 3111, Circuits 1. So I hope most of you have already taken that course because that will help you to understand some of the basic concepts which we'll not discuss in detail in this class. But if you haven't taken a course which is 3111 or something similar, please reach out to me and we can figure out if something can be done or if it is okay to take this course. But I hope most of you have already taken it. The DAD board or the Digital Analog Discovery Board is something that will be required for the labs. The versions 1 or 2 is also okay. Version 3, if you have it, then it's perfect. The parts kit is something that we already talked about, and you'll need to order your own parts. Now, along with the DAD board, I know the TAs, some of the TAs will also help you to work with some of the benchtop equipment, let's say benchtop oscilloscopes, benchtop signal generators. That we'll discuss in detail when we actually get started with the labs. But the TAs and UPIs will help you to work with some of the benchtop equipments as well, along with the DAD boards. Because you'll see the DAD board does not have a lot of accuracy. If you want to get more accurate readings, or you want to get better idea about what is actually being used in industry, some of these equipments, we have quite high-end equipments in the lab, and the TAs will help you understand and use it. I know most of you may have already used some of those equipment, but if you haven't, this course will be a good time to get started. In terms of the grades, historically, people have generally done well in the course, and I'm sure you guys will do too. In terms of the grading and in terms of how we are going to grade you, there would be 10 homeworks, almost one every week. In some weeks will not have the homeworks, but these are going to be, of course, I'll make sure that this is not hugely time consuming, but it should help you to get a better understanding of each of the concepts. So there will be 10 homework sets of 100 marks each, but we'll take the best 9 out of the 10. So it is possible that in some weeks you are inundated with other homeworks, labs, exams, and so on. And let's say you're not able to do that well in one of the homeworks. So that's why we are going to take best 9 out of the 10, and that will constitute to 18% of the total grades, 2% from each of the homeworks. There would be 7 labs throughout the semesters. And again, the 7 labs will constitute 4% each, amounting to a total of 28% for the course. And then there will be 3 exams. The first 2 will be take-homes. And first one will be at the last week, almost the last week of September. That's your exam 1, take-home exam 1. There will be a take-home exam 2, which will also be considered as the midterm exam. That will be toward the end of October. And then there will be a final exam, which I think already have been posted in Canvas. This will be in class here in Florida GM 280 on 10th of December, 3 to 5 p.m. So each of these exams, the first 2 take-home exams and the final exam, each one of them will constitute 18% each. Okay, and that's how we get to this total 100% number. So as you see that most of it is still very hands-on. The homeworks and labs, which is again take-home, and most of the lab, as you'll see that there will be an in-lab and a pre-lab component. So the labs and homeworks will constitute a total of 46%, and first 2 exams are also take-home. Only the last exam is going to be something that is in class. The grading policy, as mentioned on the right-hand side, this is just an example, but we have generally followed similar rules in the previous years as well, which is very similar to some of your other courses as well. Okay, coming to the syllabus a little bit. So today we are going to discuss the logistics, some intro to electronic circuit. From next class onwards, we're going to go much more detailed into design-oriented analysis. And by design-oriented, as I mean that eventually your final goal is to make a circuit that works. You may have components that are imperfect, but eventually you need to make it work. And how we are going to do that, that's what we'll learn in this course. Of course, we are going to use certain tools or something that you have learned before already in high school or in physics of EE or electronic circuits, for example, or Circuits1 classes. And some of them will be KCL, KVL, Ohm's law. So we are going to start very slow. We are going to start from those simple constructs and equations that you already know of. And then eventually you're going to build a much, much bigger system. We are going to talk about voltage and current dividers, amplifiers, cascade of amplifiers. And then as all of you or most of you already know about op-amps, we're going to start with op-amps. And I'll show you that there are non-ideal behaviors in an op-amp. The op-amp does not always behave in an ideal manner. So what are those non-idealities? And how does those non-idealities affect you? Or how do those non-idealities affect your analysis? That's what we're going to learn next. And then the question comes, I think most of you are already thinking that why are there non-idealities? What is the reason that we have non-idealities? So we're going into much more detail about each of those components. So what is there inside an op-amp? There could be BJTs, there could be MOSFETs, there could be diodes. So how do each of those components behave? And depending on how they behave and where those non-idealities come in, how do they affect your eventual circuit? Okay. So that's what we are going to learn throughout the semester. And for that, we'll learn about certain concepts of poles and zeros, feedbacks, coupling, and so on. But eventually, we're going to go into the details of diodes, MOSFETs, and BJTs. Now, of course, as I mentioned, that your take-home exam 1 will be between September 22 to 26. You can take that whole week to submit the exam anytime on Canvas. I'll open a Canvas link for you to submit the paper. Your exam 2 will again be October, end of October. That is also a take-home exam. And again, it will be the same process, just upload in Canvas, just like you'll be doing for all the homework assignments. Now, as we discuss some of these details about BJTs, MOSFETs, and diodes, then we'll go back to op-amps again. We'll revisit op-amps, and we'll try to see how you can build an op-amp using the components that you have already learned about in the class. So by that time, when you reach November or end of November, you'll know about MOSFETs, you'll know about BJTs, you'll know about diodes. So how to use those components to build an op-amp from scratch. That's what we're going to learn toward the end of the class. Okay, so that's going to be the overall general flow. And of course, in the process, we'll be learning about many of the components that are used inside your electronic circuits. There will be a final review on December 3rd, and as you know, December 10th will be the final exam, 3 to 5 p.m. here. These are the details of the 7 labs. Of course, they'll go hand in hand with the topics that you are learning in class. The lab 1 is basically based on Thevenin and Norton's equations, equivalent circuits, voltage and current divisions, and so on. Although we are going to start with lab 1 only in the week of September 15th, as you see on the right-hand side column of the syllabus. And then we have lab 2, lab 3, and so on. We'll also have a SPICE workshop. We already have a recorded video from previous years that you can take a look at. Also, your TAs will be helping you out and showing you how to do SPICE simulation. So what SPICE really says is if you want to simulate a circuit, if you want to simulate BJTs, MOSFETs, diodes, resistors, capacitors, and so on, if you want to simulate a more complex circuit, you want to use a simulator. Everything you cannot do by hand. You cannot do a paper-based hand design of everything. So how do you use a simulator? And that simulator is called a SPICE simulator because, again, it adds SPICE to what you are doing. And you'll see that there will be many non-idealities that you cannot even think of. And that's the SPICE you are seeing in the simulations. Okay. All right. So any questions related to the syllabus? All right. So let's discuss a little bit about the labs. The labs will be done similar to 3701. So there would be an in-lab section and a pre-lab section. The pre-lab section will constitute of 80% of the grades, whereas the in-lab section will be 20%. So before you start with the lab, please try to understand the lab manual. There will be a lab manual provided for each of the labs, and you'll be asked to do certain analysis before you actually start with the lab. And you are required to, and that handout will be provided on Canvas for each of these labs. You are required to answer those questions, do some of these analysis, and submit the pre-lab section before your actual lab starts. And that will constitute 80% of the grades in your lab. Rest of the 20%, your TAs and EPIs will ask you to do certain experiments in the lab. That's also given in the handouts. And depending on how you perform, you'll get those additional 20% of the marks. In terms of the homework, as we already discussed, that there would be about 1 homework per week and max a total of 10 homeworks, but we'll grade all 10 of them, but we'll take best 9 out of 10. Okay. Please look into the details of some of these, but anyway, these are very similar to all the other courses that you generally take. Classes, in person is highly encouraged, but if you cannot, please attend the Zoom meeting link. Of course, for certain scenarios, when I'm traveling due to university business, I'll let you know at least 1 week before so that you can plan for that. And of course, in those particular weeks, we'll be holding the class through Zoom. Okay. But that could be only 1 or 2 scenarios when I'm traveling on university business. But I'll let you know beforehand if there is a case like that. Labs, they have to be in person. They're mandatory. But I understand that sometimes because of certain restrictions, constraints, you may not be able to attend the particular lab section that you're assigned to. In that case, please talk to me, please talk to your EPIs, and maybe you can shift to a different class section or a lab section for that particular week. So we'll be trying to help you accommodate, but please talk to us if you have trouble attending one of your lab section in the semester, in the whole semester, for example. Okay, so please let us know if the timings that have been assigned on 1.0, if that works for you. If it doesn't, we'll try to accommodate. But of course, please make sure that you send us your request according to some of the constants that you might have throughout the semester. So we'll try to accommodate. All right. So I'll be uploading handouts, and I'll put as much as possible in the notes, as you'll see. So whatever we discuss in the class, most of that will be there in the handouts. So during your exams, it should be sufficient to go through the handouts and the practice problems that I'll be posting. But of course, there is a textbook, Cedra Smith. I think we didn't talk about that in detail, but it's there in the syllabus. So I'll have to open the syllabus. All right, so this is the required textbook for this class, Sedgwick and Smith. 7th or 8th edition is fine. If you have a previous edition, that's also okay. And good to have access to this book. So please practice as many problems that you can. In the syllabus, it is mentioned that the topics are from which chapters. So for example, the design-oriented analysis, KCL, KVL, everything that you'll find in chapter 1. Chapter 2 is op-amps, and some of these details, for example, chapter 5 is basically MOSFETs and so on. So please try to practice as many problems as you can from the book throughout the semester. Of course, I'll be posting more of the important problems as well as their solutions. So I'll try to make sure that most of the things are already there on the handouts. But if not, I'll mention it beforehand, and you can go on and practice them from the textbook. All right, so I'll skip through some of these other details, for example, the academic honesty policies and everything that you already know of. Makeup opportunities, of course, if there is an emergency, please reach out. We'll try to accommodate. But it's very hard generally to make a customized exam for everyone, right? So if there is a real emergency, which is approved by UF or let's say a medical practitioner, please reach out to us and we'll accommodate. Okay, now coming to some of the technical details, I'll probably talk a little bit about my background and the kind of research that we do. Again, my name is Vaibhav Chatterjee. I did my PhD from Purdue University in 2022, and then directly joined here at the University of Florida. One of the major research areas that we work on is high-speed data communication as well as powering through the body. So as you know that our body or any kind of tissue is conductive, right? So it probably doesn't happen as much in Florida, but if you go and visit some of the northern states in winter specifically, and if you touch a doorknob, you know that there is a jolt of like sudden spark or electrical current that flows, right? And that means that our body is conductive. So can you use this conductivity property of the body to do useful things? And by useful things, what I mean is that, for example, let's say you are wearing a Meta glass, right? Right now, the Meta glass sends the video through Wi-Fi to your device, let's say a mobile device or to your laptop. But Wi-Fi is extremely, extremely power hungry. And that is the reason why if you're using the Meta glasses, and many of you I know that probably have used the Meta glasses or Apple Vision Pro, something like that, what you'll see that the battery lasts only about less than 1 hour, like at best 45 minutes, 50 minutes, but not more than that, right? Imagine a scenario that you could use your Meta glasses or Apple Vision Pro for the entire day and you don't need to recharge the battery. So that is the kind of research that I'm trying to do in my lab. And the way we do it is instead of using traditional wireless communication like Wi-Fi or Bluetooth, we try to use the body as a communication medium. And our body is conductive. I don't know if you can see at the back, but this is just a simple LED light. And if I touch two electrodes, there's no button over here. If I just two electrodes and short them with my body, it lights up. So what is happening is that the electricity is flowing through my body and then lighting up this LED. And it can, you guys are welcome to try it out as well. But these are the kind of things, this is just a very simple example, but these are the kind of things that we do in our lab. So what are the, how we can design complex electronic circuit so that eventually Meta glasses or Google glasses or Apple Vision Pro, they can send the data through the body and the battery can run the whole day. That's one of the goals. Again, that's just one of the projects. If you're interested, please reach out to me. I know many of you would be interested in undergraduate research. So if you're interested in undergrad research, reach out to me. There are multiple other projects as well that we can talk about. But if you're interested, I'll just quickly show one more example of this technology. So as I said that I did my PhD from Purdue, and at Purdue, we actually built something like this that I'm going to show you next. And it's on YouTube, so you can probably also access it.
On music being transferred to the human body and through proper wire to a speaker capability. This is a standard Android phone with USB-C connector that has the body communication chip inside there. And we don't see anything playing right now. As soon as I touch, you start to hear music. Which means the music was not flowing through the airwaves like Bluetooth, but instead through my body. And you can see, even if I keep my hand up, it does not work. But as soon as I touch, it works, showing that the signals are secured in a bubble around me and is getting passed through any other conductor. Not only this works with one person, we can show the demo with David coming.
Now it gets really interesting.
Now the music is flowing from this phone to my body, to David's body, to the conductor, to the speaker capability. And if we let our hands go, the signal doesn't flow anymore, showing that there is no switch over there. It's literally the digital signals flowing through our bodies to the speaker.
All right, so that was just a brief demo. Again, something that is already available on YouTube. So let me know if you're interested in doing any kind of undergrad research with me on similar topics. So I'm mostly focusing on medical electronics with medical applications of the same technology. Yes, question. Mm-hmm. Exactly, that's a great question.
So does that mean that devices that you design have to be like ultra low power?
Exactly. That's a great question. So I'll just repeat the question for everyone that there needs to be safety limits because you are eventually sending currents to the body. So there needs to be safety limits that we need to think about. Of course, the currents that we are sending that are in the range of tens of microamperes. And sometimes even your smartwatch sends in hundreds of microampere currents through the body. And that is mentioned if you look into the documentation of your smartwatch. Right? Yes.
I was just wondering, does that technology use amplitude modulation or frequency?
Great question. So does that technology use amplitude modulation or frequency modulation? You can use both. It does not matter as much. So, but amplitude modulation or frequency modulation, any kind of analog signal modulation generally consumes more power. As one of the other questions already came in, that you need to make them ultra low power. So we generally do more digital-like modulation. We also have our own custom modulation that is not there in any of the books. So we do our own custom modulation to make sure that it is eventually much lower power than that would have been possible with analog amplitude modulation, frequency modulation, or any kind of digital modulation. That's like generally well known in the books. Any other questions? Okay, if not, let's move forward with maybe not so interesting, but more important for this course is what we're going to learn. We're going to learn about electronic circuit analysis. And if you look into, let's say, if you look into iPhone 15, for example, of course, there are it's a little bit outdated, but if you look into the circuits of an iPhone 15, you'll see that there are so many components. There are components from Broadcom, Texas Instruments, SK Hynix, Bosch, NXP, Qualcomm, and so on. So all these components, all these electronic components are eventually made of certain simple constructs. And those could be BJT-based circuits, MOSFET-based circuits, diode-based circuits. That's what we're going to learn in this course. Of course, we are not going to build anything as complex as the iPhone. There is still not the time yet. Of course, at some point, I'm sure many of you guys will do that. However, in this class, we are going to learn about simpler constructs that help the Apple designers or maybe the Qualcomm designers or ST Microelectronics designers to eventually come up with these chips, which led to the iPhone. Okay? So we're going to learn what are the building blocks and how they work. Now, there would be a lot of ways to analyze these circuits. Many of you already know about nodal analysis, loop analysis, etc. Now, for a given circuit, some ways will be simpler than other techniques. Right? For one particular circuit, maybe nodal analysis is simpler. For some other circuit, maybe loop analysis is simpler. Maybe you can convert one form of circuit, let's say a delta circuit to a Y circuit, and then it becomes simpler. So in this course, we are not limited by, I'll never ask you in the exam that, oh, do the analysis in this particular manner. You are free to do in any way that is useful and that is easier for you. Again, what is easy and what is hard can be very different from one person to another. So I'll give you that liberty. Do the analysis in whatever way you think is easier for you, but come up with the right answer. Design-oriented, task-oriented, and result-oriented. We want, finally, as a design engineer or someone who is in the industry, people would want that, yeah, you should be eventually able to make one of these chips for the iPhone, let's say. So that result is important. And how you come up with it, there could be dozens of ways. Some ways could be easier, so that's why we are going to learn about easier ways as well as more complex ways. But eventually, it's up to you which one you are going to prefer. So initially, what we'll start with, again, very simple voltage divisions, current divisions, and that's what I'm going to talk about in the next 10-15 minutes in the class. Thevenin's and Norton's theorems as well, which we are going to discuss in the next lecture. So let's start very slow. Let's start with Ohm's law. You know what Ohm's law says is the current, the electrical current flowing through a conductor is basically a ratio of the voltage and the resistance of that conductor, right? Or in another way of speaking, that the voltage developed across the conductor is a product of the current flowing through the conductor and the resistance of it. So that's what Ohm's law will tell you. What does Kirchhoff's current law tell you? KCL, that you cannot create or destroy currents. The total summation of all the currents in a node will be same or will be equal to 0. So if you take the so basically all these currents, let's say incoming currents I1, I2, and there are outgoing currents I4, I5, and I3. The total summation, if you take the direction into consideration, so let's say I1 plus I2, but then minus I3, minus I4, and minus I5, because these are outgoing currents and these are incoming currents. So the total summation will be 0. The other way of saying it is the summation of the incoming currents will be equal to summation of the outgoing currents. Similarly, KVL or Kirchhoff's voltage law tells you that the total voltage in a loop is equal to 0, right? So there could be a voltage source. For example, this could be a voltage source, and there could be two consumers of that voltage. And by consumers, in this case, I am talking about resistors, which are basically consuming some amount of power or current that is being generated from this source. And the total voltage developed across the resistors on the top and on the right, the total voltage summation is equal to the original voltage source's voltage. So minus V plus V1 plus V2 equal to 0 again. Or V, or the voltage source, will be equal to the voltage drops across the two resistors. Again, most of you already know this. You already know about voltage divisions. Let's say I have a voltage source over here, Vi or V input, and then you have these resistors, Ra and Rb. Now, of course, from Kirchhoff's voltage law, maybe it's better if I write something down here. Let's see. So from Kirchhoff's voltage law, you know that if the voltage developed across this resistor is Va and the voltage developed across this resistor is Vb. So from KVL, you know that Vi will be equal to Va Oops, maybe I should use a different color. So let's call this VA. And let's call this VB. And from KVL, you already know that VI is equal to VA plus VB. Now from Ohm's law, you know that VA, the voltage developed across this resistance, will be a multiplication of the resistor and the current that flows through it, that Ohm's law. From VB, you know that VB is multiplication of RB and the current that flows through this. Now from KCL, you would be able to say that the current that flows through RA, the first resistor, is same as the current that flows through RB, because there is no other path for the current to go. So the current is same in RA and RB. Let's call that current equal to I. Okay. So your VA plus VB will be nothing but I times RA plus I times RB. So now if you take I common, then that becomes I times RA plus RB. And that is the reason why when you see two resistors in series, the equivalent resistance is basically an addition of them, basically an addition of RA and RB. So VI, the voltage over here, would be I, that is the current that is flowing in this entire loop, multiplied with RA plus RB, which is a combination of those two resistors in series. Another way of saying it is that the current is VI divided by RA plus RB. And this is basically the proof that series resistors add up. Right? And we proved it from Ohm's law, KCL, and KVL. Now, what is the voltage developed across each one of them? So if you look into, let's say, the voltage at this node, and let's say this is my ground or the common reference point. Now, in any electronic circuit, you'll know that there needs to be a common reference point, which we generally call as the ground. Okay? So let's say your ground is over here. So the voltage, if you say that this is my output voltage, so that is the voltage across RB. So whatever voltage is developed across RB, you're calling that your output voltage. You could have called the other voltage, the voltage developed across RA, as your output voltage as well. But let's say you want your output voltage to be the one that is across RB. So what would be that voltage? That would be the current multiplied with RB. I multiplied with RB. You already know what I is. I is VI divided by RA plus RB. So VI divided by RA plus RB, that's your I, multiplied with RB. That's basically your voltage across RB. So the important conclusion from here is that the voltage across each resistor is proportional to the resistor's value. The voltage across the RB resistor is directly proportional to RB, because the current was VI divided by RA plus RB, multiply that by RB, you get the voltage across RB. Similarly, if you wanted to find out the voltage across RA, that's current multiplied with RA, and the current is VI divided by RA plus RB. So this part remains same, only that this numerator RB will become RA when you want to find out the voltage drop across RA. So the voltage across each resistor is proportional to the resistor's value. That's one important conclusion from here when you think about voltage division. So any voltage, that would be proportional to the value of the resistor. If you think about current division, and again, you can prove this equation through Ohm's law, KCL, and KVL, that if you, and we can do it here in the class as well, because we have maybe 5 minutes left. So let's try to do that. So let's say this is your current, and that current is getting divided into two parts, one flowing through the RA resistance, one flowing through the RB resistance, right? Now, the voltage across both RA and RB is equal, right? So because this is the node, this is the same common node, this point and this point is same as the top node and the bottom node of the RB resistor. And you know the way the voltage is defined is basically a potential difference between two nodes or 2 points in the circuit. So because the top nodes are the same point and the bottom nodes are the same point, the voltage is same across RA and RB. So what would be the current that is flowing through RA? That would be, let's say, the voltage at this point divided by RA. That is the current flowing through RA. And what would be the current flowing through RB? That would be voltage, that is the voltage at this point, assuming that this bottom point is grounded or equal to 0. So the voltage across RB, that is V, divided by the value of RB, that will give you the current through RB. Again, Ohm's law, right? Nothing more than Ohm's law. you add those two currents up, V over RA plus V over RB. You add those two currents up, you get the total current. So the total current was anyway getting divided into two parts, one through RA and one through RB. This is the part that was going through RA. This is the part that is going through RB. So what is the total current? That is V times 1 over RA plus 1 over RB. And this is what a parallel combination of resistors look like. Again, proof of two parallel resistors RA and RB is equal to 1 over RA plus 1 over RB. And you can write that in the form of V times RA plus RB divided by RA times RB. Right? So voltage multiplied with this resistor value. That is equal to your current. That is equal to your total current. So this is equal to your total current, which is equal to voltage multiplied with RA plus RB divided by RA times RB. Now let's think about Ohm's law again. Current is equal to voltage multiplied with some quantity. Or in other terms, voltage is current multiplied with some quantity. And that will be called the effective resistance. So what would be the effective resistance? The effective resistance will be 1 upon this quantity that you have, because this is current equal to voltage multiplied with a conductance quantity. This is not resistance, because voltage multiplied with conductance will give you current. Current multiplied with resistance will give you voltage. Again, simple Ohm's law. So what is the effective equation for two resistors in parallel? That would be RA times RB divided by RA plus RB. So that gives you the effective parallel resistances value. Now again, you can find out what is the individual current through those two resistors, IA and IB. So if you write down IB, so your IB will be equal to the voltage that you develop, or let's say, so this is the voltage and this is the total current, and total current gets divided into two parts. Now the current that is flowing through IB, that is equal to this current, the total current II, that's the input current, multiplied with RA divided by RA plus RB. Why is that? Because this is equal to voltage divided by RB. So the current that is flowing through RB, that is the voltage developed across RB divided by RB. And what is the voltage developed across RB? That is I, the input total current, multiplied with RA/RB divided by RA plus RB, right? Because this is the total amount of resistance, or the effective amount of resistance that you see looking from this side towards the right. So the total resistance was RA/RB divided by RA plus RB. Multiply that with total current, you'll get the total voltage. Now divide the total voltage with RB, you'll get the current that is flowing through RB. So voltage divided by RB, that is IB, and that can be written in the form of II times RA divided by RA plus RB. So what we learned here, the most important thing that we learned here is that the current in a branch is proportional to the resistance of the opposite branch. The current through IB is proportional to RA. It's not proportional to RB. And that makes sense, right? Because resistance will stop current to flow. So if you have a higher resistance, your current will be lower. And if you have a lower resistance, your current will be higher. And that is the reason why the current is proportional to the other resistance. So let's stop here. And in the next class, we'll start with more detailed discussions about this.